Hey everyone, welcome to day 27 of Math 133. We are getting toward the end. Today is the Chapter 11 project, and then do the 11.3 lecture notes and the Chapter 11 flowchart lecture notes. And that is the last of the lecture notes. So, uh, next Thursday, we're just going to look at the Chapter 11 review. So, yeah, like I said, we're getting toward the end. Next week is the final exam. So it's going to be on Thursday if you're doing it with me, or you can take it at the testing center. On Tuesday next week, we're going to cover the sample final exam. And we'll cover actually a little bit of it today and a little bit on Thursday as well, because it's pretty big. It's 14 pages, and I'm certainly not going to be able to cover all of that on Tuesday next week. So we'll do a little bit tonight. And then any that we don't get to cover, Cindy and Elaine, they'll get a chance to work on it with you on Monday and Wednesday next week. So if you come to the class this week, then you get your participation points. If not, make sure you fill out the discussion board. This is the last week for discussion boards. Next week, there's no discussion board. So if you don't come to the class next week, that's fine. Just make sure you take the final exam. Okay. That's important. Um, anyway, the final exam is going to be 12 pages. So the midterm, if you remember, that was 9 pages. So if you ran out of time or you were close to running out of time, you might consider taking the final exam at the testing center where there's no time limit, okay? Because even though, the midterm was 9 pages and you had 3 hours, the final exam is going to be 12 pages and you still only have 3 hours on Zoom. Okay. So if you finish with plenty of time, that's not a big deal, but uh, you might want to, definitely consider taking it at the testing center if, if you were close to, or if you did run out of time. Okay. Okay. Uh, Today we're going to do the Chapter 11 project, which is on page 578 in your course pack. Also, if you click on the Chapter 11 project in Canvas, there's going to be two links to StatCrunch that you're going to need. One of them will take you to random confidence levels, and one will take you to random levels of significance. And yeah, those are closely related, but remember, confidence levels are large numbers like 86, 70, 90%. Okay. Um, so I need to make sure I click on these. I actually click on it. So there we go. Um, yeah. So we're gonna need those in a little bit. Okay. But the chapter 11 project starts on page 578. Okay. All right. So we're going to be looking at M&Ms and M's and Skittles again, but this time we're actually going to look at them together. Okay. In the previous projects, we did like confidence intervals for M&Ms, and M's, and then we did a completely separate confidence interval for Skittles. Okay. This time we're going to be comparing the two. Okay. And that's what chapter 11 is all about. Chapter 11 is all about you have two different samples and comparing and contrasting them. Are they coming from the same population? Are they significantly different? That kind of thing. Okay. Okay. So, uh, fill out the table with the number of candies in the whole bag. Um, Portion of the four different colors that are shared. So now we finally get to explain why we needed you to pick Skittles that were the same color as the M&Ms, right? Because we needed green for both of the samples, orange, red, yellow. There's no blue Skittles or brown. I guess brown would be pretty gross, but there's at least a couple that are matching. Okay, so that's important. All right, so we're going to fill in our numbers. So first of all, uh, N1, this is the sample size for M&Ms. So we're gonna need to pull up our M&M data, okay, wherever you have that. So here's mine. All right, so I had 145 M&Ms. I had 22 green and then 29 orange. Red was 17. Why are these not in the same order? This is not alphabetical. All right. All right, so there we go. I've got my M&M numbers here, okay? So for each of those, I need the proportion for M&Ms. So remember P hat is your X value, so 22 divided by 145, okay? Now you can type all those in, but I'm lazy, so I'm gonna go to Google Sheets and hit the big plus right here for a blank spreadsheet. And I'm just gonna fill it in here because it'll be a lot quicker. So I got green and orange and red and yellow. And I got 22, 29, 17, and 28. Okay. So now my proportion is going to be equals, and then I'll click on the 22 and divide it by my total, which was 145. And yes, Google Sheets, that is correct. I do want all of those divided by 145. So now I've got those, and I can just fill those in. So 0.152, 0.200, 0.117. Okay. All right, great. So now I need to do the same thing for Skittles. So for Skittles, I had 241. And then, let me see here. I had 51 green, 54 orange, 47 red, and 55 yellow. Now, obviously, you guys are going to have different numbers, which is totally fine. Okay. All right. So now that I've got that, let me type those into my spreadsheet. So for my Skittles, I had 51, 54 for orange, 47, and 55. Okay. So this is going to be equals, and then this one divided by 241, which is my total for Skittles. And there's my proportions for Skittles, 0.212, 0.224, 195. Okay. All right. Lastly, we need to calculate the difference between the two. So for green, we'll take the p hat for M&Ms, 0.152, and subtract it from the p hat for Skittles, which is 0.212, and that'll give us some difference between the two, okay? So I can do that here by doing equals, and then I'll click on the proportion for M&Ms minus the proportion for Skittles, and there's my differences, okay? So obviously you don't need to fill these in, but you can. PM, XS, PS, and difference. Okay. You don't need to put in titles. I just need to write down what these numbers are. So some of them are going to be negative. So make sure you write it as negative. So negative 0.060. So that's, and yours are going to be different, obviously, because you had different numbers of Skittles, which is fine. Okay. 0.078, negative 0.35. There we go. So what was the point of that? Well, what are we trying to do, right? So what we're trying to do is we're trying to compare the sample from M&Ms and the sample from Skittles and see if the proportions are the same. Okay. Now they're not going to be exactly the same, but are they close enough that we can call them, you know, approximately the same? Okay. So in other words, is the proportion of green M&Ms the same as the proportion of green Skittles? Okay. Now, we can't do that for the entire population because we can't look at every single M&M, but we can use our sample to approximate the population, right? So that's the idea. So if this p-value and this p-value are the same, then when you subtract them, you get 0. Okay. So if we get numbers that are close to 0, that means that the two populations are close enough that we can consider them the same. Okay. Now, for M&Ms and Skittles, we know that that's not the case, right? We know that for M&Ms, the proportion of green M&Ms or red M&Ms or whatever color you want is 1/6, which is 0.6, so it's 16%. Okay. And there's 5 colors of Skittles, so the proportion for Skittles is 1/5, okay, which is 20%. So if we were to subtract those, we don't get 0. Oops, that was not typed right. There we go. There we go. 1/6 minus 1/5 is negative 0.3%. So it's 3%. Okay. So the proportion of red M&Ms and the proportion of red Skittles is not the same. Okay. Now we know that because we know M&Ms and Skittles are produced in the same proportions. But in practice, if we were looking at something else, we wouldn't know those true proportion values. Okay. Like let's say we were comparing two COVID tests, or not COVID tests, COVID vaccines, right? Back when they started producing vaccines, there were a whole bunch of them, right? There was Pfizer and what was the other one? It was started with M. Um,
Johnson and Johnson, and I believe Moderna.
Moderna, that's the other one. Yeah. So if I wanted to compare which of those vaccines was the most effective, I can't check that against the entire population because in order to test that against the entire population, I have to vaccinate everyone. And we already know that there's going to be people that don't want to do it. And it also takes time to produce that vaccine, and you have to test and make sure it's safe and things like that, right? So, if I wanted to figure out which, of those vaccines was the most effective, I would have to do a sample and I would compare this population and I compare this sample and I give them the Pfizer vaccine, and then I compare this sample and I'd give them the Moderna vaccine, and I would see if those proportions, what proportion of them got COVID after the vaccine and what proportion didn't. And then I could subtract those and see, okay, are those significantly different? Is one better than the other? Okay. So that's the idea that we're looking at. We're comparing these two samples. Okay. Now, when you do that, you can do it one of two ways. We have to check and make sure that it's independent of each other. So we'll talk about that in a second. But what I mean by that is you need to make sure that no one in your two samples are in both samples. If you have a person that's in both samples, then that means you're going to give them the Pfizer vaccine and the Moderna vaccine. And then if they don't get COVID, you don't know which of the vaccines actually prevented it. Okay. So uh, we'll talk about that in a second. Okay. So when you're checking to make sure you have, which proportion is better, which one's higher, what's the difference? Is the difference close to 0? You need to make sure that you're selecting your samples so that they are independent of each other. Okay. Now that's not a problem with M&Ms and Skittles. There's no way that you would have a candy that is in both bags. Like you're never going to find an M&M in your Skittles bag. Okay. If you ever do, I probably wouldn't eat that. So anyway, okay. So now that we've done that, question two, circle the color that showed the largest difference in proportions between M&Ms and Skittles. Okay, so ignoring the plus and minus, okay, which one of these is the biggest? So the biggest one for me, this one's 6%, 2%. Biggest one for me is negative 0.078. That one's the biggest for me. So that one is red. So we're gonna use that for part four. Okay. Circled the color that showed the second largest difference in proportions. Again, ignoring the plus and minus. Which one is the second largest number? So mine is green. Okay. And we'll use that for parts two and three. So we're actually going to use this one first. We're going to use green first. At least I am. Yours are obviously going to be different, but we're going to be doing stuff with the color from number three first. Okay. All right. So I need to make sure that's where I can get to it. Let's go to page 579. All right. Use the StatCrunch file to get two random confidence levels for this project. Okay. So we need some confidence levels. So you're going to go to Canvas. You're going to click on the Chapter 11 project. You're going to click on this first link, Random Confidence Levels. It's going to bring you here to StatCrunch, and you're going to pick two of these numbers at random. And you'll do that by selecting Data, Sample, and then select Confidence Levels and 2. We're going to select 2 of these, okay? So write those. All right, so I got 73.8% and 94.3%. Okay, so there's that. Next, use the StatCrunch file, random levels of significance to generate a random level of significance. Okay, so same thing, we'll go to Canvas, select the second link for the random levels of significance file, and that's here, okay? And if you get them mixed up, so confidence levels and significant levels of significance are very closely related. Your confidence level plus your level of significance adds up to 100%, okay? So your confidence level is how confident you are in your results, okay? The alpha, the level of significance, your alpha is what chance you have of making a type 1 error. So it's basically, I'm 95% confident, which means there's a 5% chance I'm going to make an error. Okay. So basically, the main thing to remember is confidence levels are big. You want to be very confident, right? 70%, 74%, those are terrible. I like to be in the 90s, so 95, 99%, that's very confident, okay? On the other hand, your level of significance, that's your chance of making a error, a type 1 error, and we don't want errors. So level of significance, your alpha is going to be a very small number, 10%, 5%, 1%, things like that, okay? All right, so go to data, hit sample, level of significance, we want a sample size of 1, and I got 4%, 0.043. All right. So there we go. Now you're going to have different numbers because you're picking it at random. StatCrunch is randomizing it for you, and that's fine. Okay. The projects give you a chance to try doing things with your own numbers as opposed to, just copying what I have. Okay. Confidence interval for M&Ms and Skittles. All right. So you want to construct a confidence interval for the difference in proportion of M&Ms and Skittles for the second largest color. So the second largest color for me, number 3, was green. So I'm just going to make a note here. I'm doing green on this one. Verify whether all requirements are satisfied for constructing this confidence interval. Okay. So all of this information that we're going to be talking about today in our exam notes packet is going to be coming from page 264. Okay. So test for the difference between two independent proportions. Okay. Now, previously on like this page, when we're doing hypothesis testing for a single proportion, that's if you have one sample, right? Proportion stats, one sample with summary. We now have two samples and we're looking at them together. So proportion stats, two samples with summary. Okay. So the checks that we need to do to make sure that we are satisfying the central limit theorem are very similar. We need to check that it's random, independent, and normal, but there's a little bit more to it because first of all, we have to make sure that both samples are random. We need to make sure that the samples are independent of each other, and we need to check both samples are independent of the population. And lastly, we need to check that both samples are normal. Okay, so there's a bit more that we need to do, but it's going to feel very similar. So first of all, we need to check that it's random. Okay, so both samples are random because every candy had equal chance of being selected, right? Or equal chance of ending up in our bag, right? However you want to word it, okay? We didn't bias the sample here by, picking specific colors, okay? Next, we need to check that that is not how you spell it, pendant. We need to check that the samples are independent of each other, okay? Or they need to be dependent of each other, okay? And that would be on, I believe, the next page. Let's match pairs. That's okay. Anyway, so there's two ways you can do a test or a confidence interval or whatever you want to do when you have two samples and you're comparing the two samples together. The first is they're independent of each other. In that case, you have two groups. Each of them is measured once. Okay. So that's one option. Okay. Two groups measured once. And that's what we have in this case is we have two groups and there's no overlap. Okay. The other option is dependent. And in that case, you need one group measured twice. Okay. And in that case, you need everyone in the first sample has to also be in the second sample. So an example there would be if I gave everyone the first vaccine shot for COVID, and then they had to come back for a booster, right? I would, if I'm testing to see the effectiveness of that vaccine, and I'm including the booster shot, I need to make sure that everyone in my test gets both shots. I need to make sure that you get the first shot and then come back a couple weeks later and get the booster. If there's a person in your sample that just gets the first shot and doesn't get the booster, then if that person gets COVID, you're not going to be able to tell if if they would have been protected by the booster or not. Okay. It's going to mess up your results. Okay. So you need to measure everyone the same way. So anyway, we'll see more of that when we look at the chapter 11 review. Okay. But for now, all we need to say is we've got two groups. There's no overlap. They're measured once. We're good there. But we also need to check that they are independent of the population. Okay. So to do that, that's the same thing that we've done before. You check 20 times n, and that needs to be less than the population n. But you need to do that for both the first sample and the second sample. Okay. So you can do M&Ms if you want, or you can just write 1, however you want to do it. I'm going to put M and S just to remind myself that I got to do it for M&Ms and I got to do the same thing for Skittles. So my sample size was 145 and the population is all M&Ms. So this is 2900 and that is less than the number of M&Ms. But I also have to do this for Skittles, which is 241 is less than all Skittles. We gotta check if that's true. So this is 4820. Is that less than the number of Skittles? Yes, it is. So both of those are true. So I have a yes. Okay. All right. Lastly, I got to check if both samples are normal. So I need to check n times p times q. Okay. And that needs to be bigger than 10. So I need to check that for M&Ms. And I also need to check that for my second sample, which would be, in this case, Skittles. Okay. All right. So my M&Ms, I had 145. All right, I'm doing green, and my green M&M proportion was 0.152. So what's my Q then? Let's see. 1 minus 152 is 0.848. All right, so I need to multiply these two. So 145 times 0.152 times 0.848 gives me 18.7. That is bigger than 10, so that's good, but I can't say yes yet. I got to do this for Skittles as well. For green again, my green portion for Skittles was 212. 212. 0.788. All right, 241 times 0.212 times 0.788. 40.3, and that's bigger than 10. So yes. All right. If we'd gotten one of these as a no, then the whole thing is a no. And so we would need to stop here and we would need to fix that, or we wouldn't be able to construct a accurate confidence interval. Okay. So we could, if we didn't have enough M&Ms, like if this had come out as 8.7 instead of 18.7, I would have to redo this and go get some more M&Ms. Now, the question is, would I have to throw out my previous M&Ms, or can I just go buy another bag and mix it in with the ones that I already have? And the answer is, well, as long as it's random, random plus random is still random. Okay. So as long as I don't have any bias, it's fine if you just add the previous uh, selected sample to your new one. Okay. That's important because, it's cost money to buy more M&Ms. It's gonna, if you had to, vaccinate more people, it's gonna take time, it's gonna take money, right? All right. So for our case though, even if you have a no, regardless of whether or not the requirements were met in number 6, we're going to push forward and we're going to construct a confidence interval for the difference in proportions of my chosen color. My chosen color was green. I'm just going to remind myself. For green, M&Ms and Skittles using confidence level number 1. Confidence level number 1 for me was 73.8%. Okay. All right. So do not show any work. So if we had a single sample, which is what we talked about in chapter 9, I'd want you to write the formula and then do some substitution and then the result. Okay. And in this case, we don't have the formula written on the exam notes packet. And that's because the formula is a little bit complicated. It's not anything outrageous. It's very similar to the formula for a confidence interval that we talked about in chapter 9. But if you know how to do it from chapter 9, it's not really worth adding more complication because it's basically the same. Okay, just a little more to it. So we're just going to use StatCrunch and have StatCrunch give us the answer. Okay, so all right, we're going to do stat proportion stats to sample with summary. Okay. All right. So where's my StatCrunch? StatCrunch. So log into StatCrunch. And then once you've logged in, you can hit this big orange button and we'll do stat proportion stats to sample this time with summary. All right. And I had for green, I had 22 M&Ms out of 145. I had 51 green Skittles out of 241. We'll do hypothesis testing in a little bit, but I want, in this case, to check the button down here for confidence interval. And I'm going to use, my confidence interval is going to be 73.8%. That is a terrible confidence. 70% confident. I'm 27% not confident. All right. Hit compute. And I don't need all of this stuff. I just need my upper limit and my lower limit. My upper limit and all right, my lower limit here is 0.104, so 10%. And my lower limit, oh, 5 decimal places? Holy smokes. All right, all right. 0.148. And my lower limit and then up 0, 1. All right, so my upper limit is close to 0. It's only 1.5%. All right, there we go. I missed a parenthesis. So what have we done? What have we accomplished here? So what we did was we took a sample of M&Ms, took a sample of Skittles, and we found the proportions. And so in this case, I'm looking at green, and I want to look at the difference between the two. And I find that the difference is negative 0.06. Okay. Now, if these two proportions are the same, this number minus this number, if they're the same number, I get a number that's close to 0. Now, they're not going to be the same because it's a random sample, but are they close enough to 0 that I can say, yeah, the proportion of green M&Ms and the proportion of green Skittles is the same, okay? Well, that would require that my confidence interval contains the number 0. So I am 73%, 73.8%. I'm 73% confident that the true difference between the proportion of green Skittles and the proportion of green M&Ms is somewhere in this range, somewhere between negative 10% and negative 1.5%. Okay. Now that's a pretty big range. Okay. But the true number is in there, right? We had said earlier that the true value, which we know is 1/6 minus 1/5, is negative 0.03. Okay. So that number is in this range. Okay. Um, but the question is, uh, are the proportions significantly different? Okay. So here's what Willy Wonka says. Willy Wonka claims that M&Ms and M's and Skittles have a significantly different proportion for your chosen color. So I chose green. He says that the proportions are not the same. Okay. Does your confidence interval support his claim? Well, if if they were the same, then when you subtract this proportion minus this proportion, you get zero. So really what we're testing is whether zero is in the interval or not. Right? Here's my number line. Here's zero right here. Okay? 0.0. Now, my confidence interval goes from negative 10% to negative 1%. And so here's my confidence interval. I am 73% confident that the true difference falls somewhere in this range. Well, zero is outside of that range. Okay. So I don't know what the true value is. Okay, well, we actually do, but pretend you didn't. I do know that if it's in this range, it's not zero. Okay. So he is saying that they are significantly different, and I will support that claim because zero is not contained in the interval. Okay. Now, on the other hand, if one of your numbers is negative and one of your numbers is positive, then that means that zero is in the interval, in which case you would say do not support because zero is not contained in the interval. Okay, so what your answer is one of these two. Okay, depending on whether, you know, whether zero is in your confidence interval. Okay. All right. Now, this confidence interval is pretty wide. And it's actually pretty wide, even though I have a low confidence interval. I have a low value of 73%. If I was looking at like a 95% confidence interval, my range would be even wider. Okay. So I don't like that. So let's say that we use our proportion of M&Ms and M's and Skittles for the second largest difference. So we're still using green in my case. But now I'm going to use confidence level number two, which is going to be 94.3%. So let's say I wanted to get a better confidence interval. Calculate the minimum bag size for each type of candy required to ensure that the difference in the proportion of the second largest color for M&Ms and Skittles is within a 2% margin of error. Okay, so my margin of error here, I'm going from negative 10 to negative 1. That's a 9% range. Okay, so even if I cut that in half, it's, a 4.5% margin of error. That's too much. Okay. So if I want to be more accurate, I would want a smaller confidence interval. So I want it to be like a 2% range. Like I want it to go from, you know, 5% to 1%. That's only a 4% range. Okay. So to do that, I need to do a new sample with more M&Ms and more Skittles. How many more? That's what we're going to calculate here. Okay. So that is on page 261. Now, page 261 has the sample size formulas for a single population proportion, but down here it has the double population sample size formula. Okay. And they're very similar. So it's p hat q hat z alpha over 2 squared over the margin of error squared, right? Same thing. I still have the z alpha over 2. I still have the margin of error. I still have the square. It's just that now my p hat q hat includes a p hat q hat of both samples. Okay. If I don't have a prior estimate, instead of a 0.25, I use 0.5. Why is that? Well, that's because if you don't know, if you don't have a prior estimate, you just use 50%. So we'll say 50%, 50% plus 50% times 50%. You multiply those all out, you get 25 plus 25, which is 0.5. Okay. So it's the same formula, actually. It's just using 50% for everything if you have no clue. We do have a prior estimate, whatever you have on the first page. These are my prior estimates for p hat and uh, m and p hat s. So I need my formula, and we'll substitute in, and then we'll get our result. Okay. All right, so my formula is n equals n1 equals n2 equals p hat 1 q hat 1 plus p hat 2 q hat 2 alpha over 2 margin of error squared. Okay. Now, what's going on with this n equals n1 equals n2? Like, why is that all there? So we need to redo our sample. Okay, we're not happy with our confidence interval. It's too wide. We want to be more accurate. So I need to redo the sample. So I need to redo both samples. So how many M&Ms do I need to select? How many Skittles do I need to select? Okay, that's what's happening here. And it's going to be the same number. That's why you have all this. Okay. So anyway, we can simplify it a little bit. So we'll just write n equals, and then we'll plug in our numbers. So my p hat for M&Ms was 0.152, and my q, I had that written on the previous page, 0.848. For Skittles, it was 212 and 788. My margin of error is 2%, which is as a decimal, 0.02. And now I need my Z alpha over 2. So I'm going to use a 94.3% confidence interval. That's what I'm using. You probably got a different random number, which is fine. So you're going to come over here to StatCrunch, and we'll do stat calculators normal. We click on between, and we put in our confidence level here. Mine was this one. Okay. And so my Z alpha over 2 is 1.9033. Okay. That's all stuff that we covered in chapter 7, right? So, okay. So now that I've got all this craziness, I need my result. So here we go. So let's put this in here. Parentheses are all in the right spot already for me. So 0.152 times 0.848 plus 0.212 times 788. Close my parenthesis, open a new parenthesis, and then I have 1.9033 divided by 2. Close that parenthesis, and then I square it by holding Shift 6, and then square that, and I get 2680.25. Okay. Now that's not my answer. Okay. What I was trying to do was I want to do a new confidence interval. I want to be more confident. I want to be more accurate. I want to be within a 2% margin of error. So this is my minimum sample size. But since it's a sample size, I can't have a quarter of an M&M. So I need to round this to the nearest number. Now, when you're doing a sample size, we always round up. okay? Because if you rounded this down, you wouldn't be at a 2% margin of error anymore. You'd be at like a 2.1%, okay? So rounding it up is fine. Now I'm at a 1.99% margin of error. Lower error is better, okay? So even though it's going to mean I need to sample a little bit more, I mean, you only need to sample one more as opposed to rounding this down. We always round our sample sizes up. Now this is not 2,600 candies. I can't mix and match the M&Ms. This is 2,681 M&Ms. And I also need 2,681 Skittles. Okay. I need to do both. So if you don't write both, if you just write this number, that's not the whole thing. Okay. Okay. So, and by the way, this number right here, if I wanted to redo this sample, um, I can't go to the store and ask them, hey, I would like to purchase 2,681 random M&Ms. Gonna kick you out of the store, right? You buy the bag and you get what you get, right? So if you were trying to redo this and to get a better confidence level, how do I do that? Well, this is just your minimum sample size, okay? What you do is you'd go to the store and you'd buy a bag of M&Ms and you count them. And if you end up with not enough, like if you have 2,000, you would need to go and continue buying more and keep adding them to your sample until you're over this. Now, what if I go over this? What if I'm at 2,700? That's still fine, okay? That'll actually get you an even better margin of error, okay, or a better confidence level. Both of those are good things, okay? This is just the minimum for having a 2% margin of error, okay? So, yeah, in this case, we don't have control over how many numbers are in a bag of M&Ms, but we can just keep buying more if we need to, okay? Until we are somewhere over this. All right, so now that we've done that, let's move on to some hypothesis testing. Actually, no, we got two more questions and then we'll do some. Page 581. Suppose when you were completing number 9, you had no prior estimates. Would your sample sizes have been smaller, the same, or larger? So we used prior estimate from what we measured. What if we had no prior estimate? Would it be larger, smaller, or the same? What do you guys think? You guess if you're not sure.
Larger.
I agree with that. So you can write on your paper here that no prior estimate is always going to be larger than having a prior estimate. Okay. Suppose when completing number 9, you'd use confidence level 1 instead. So for me, uh, I used 94%, but if I had used this one instead, this is a smaller confidence level. So I would have ended up with a smaller sample size. Okay. Um, Now, if your numbers are flipped, or if you watch the video from this morning, I had a bigger number here. And so if this is a bigger number, then you would be using a larger result. Okay. So you're basically just going to circle if this one is smaller or larger than the one that you did. Okay. All right. All right, so now that we've done that, we're going to do some hypothesis testing. And you'll notice that hypothesis testing is very similar to confidence intervals. Earlier when we were talking to Willy Wonka, he was saying that they are significantly different. The two populations have different proportions. Um, and that's basically a hypothesis that we could have tested, and you would support or not support, or in other words, reject the null or not reject the null, depending on whether you support his claim or not, right? So hypothesis testing and confidence intervals, they're really the same thing. And they have a lot of steps that are the same. In fact, we've already seen that when we do this in StatCrunch, we're going to do stat, proportion stats, to sample with summary, and then you check, do I want to do hypothesis testing or check the bubble for confidence interval? So, yeah. Anyway, it feels a little different because your results are different, but you're doing the same steps. You're doing the same things. So here, you want to conduct a hypothesis test for the difference in proportions of M&Ms and Skittles. This time for the largest difference of color. So number 2 for me was red. So this time I'm doing red. Verify whether all requirements are satisfied for conducting this test. So your steps for that are going to be very similar when you are conducting the confidence interval and checking to make sure you satisfied the central limit theorem. It's pretty much going to be the same thing. You gotta check if it's random. So yes, because uh, both samples um, are random. Because every M&M and Skittle had equal chance of being in our samples. Independent. We have two groups measured once. Independent of the population. We do 20N1. That has to be less than N1. 20N2 has to be less than N2. So let's see here. I had 2,900 is less than all M&Ms. And 4,820 less than all Skittles. So yes there. So the only one that's going to be different is the normal part, and it's only different because I'm not using green anymore. This time I'm using a different color. So I need to check N1, P hat 1, Q hat 1, and N2, P hat 2, Q hat 2. And since I'm doing red this time, my P hat is 0.117, 0.883, 241 times red Skittles 0.195. Let's see here. 1 minus 0.805. All right, so 145 times 7 times 0.883 is 14.9, which is bigger than 10, so I'm good there. 1 times is 37.8, and that's bigger than 10, so I'm good there. So I got two yeses. So there we go. All right. All right, so that was a lot of work. But now that I know that those are all true, those are all yeses, that means that I can do a hypothesis test with accuracy. Now, even if you got a no, we're going to keep going. Actually, it doesn't say regardless of whether you met the requirements, but all right, test whether there is a significant difference between the proportions of M&Ms and M's and Skittles that are the largest difference color. So I'm doing red for mine at a level of significance from number one. Level of significance, mine was 0.043. So that's going to be my alpha. Okay. But step one, writing out our null hypothesis, is P1 minus P2 equals 0. Okay. Now you don't have to write 1 and 2. You can write M and S if you want, or you can write 1 and 2. That's fine. Uh, Now, how do I know whether the M goes first or the S goes first? The answer is it doesn't really matter. And you don't even necessarily have to write this minus this equals 0. You could write P1 equals P2. That's the same thing as what I've written here. It's just that if I subtract P2 from both sides, I get P1 minus P2 equals 0. Okay. So however you want to write it is fine. Okay. As long as when you get to the alternative hypothesis, you make sure that if it's a left tail or a right tail, then it does matter which one comes first. Okay. Um, so PM minus PS. Now for me, am I looking at more than, greater than? I'm not. I'm just looking whether there is a significant difference. So I'm really just checking if the two are not equal, if the subtraction, if the difference is not 0. Okay. So mine is going to be a two-tailed test. Okay. Yeah. Now step 3 in chapter 10, step 3, we wrote out the formula for the z value. And we're not going to do that here. We're just going to pull it in from StatCrunch. Um, because like I said before, there is a formula for it. And it's very similar to what we learned in chapter 10, but we're not going to make you, learn that part because it's a pretty complicated formula. It's basically just take the one from chapter 10 and double it, which, is a lot. So anyway, so we're just going to fill that in from StatCrunch. All right, and we're going to fill in our p-value from StatCrunch as well. Okay. So let's go do that. Let's get stat, proportion stats, to sample with summary. And I'm filling in my numbers for red. Red was 17, 145, and then 47 out of 241. So this time I am doing hypothesis testing. And you'll notice that they write it in StatCrunch a little different than on our exam notes packet. But like I said, that's the same thing. So if you want to write P1 equals P2 for your null hypothesis, that's the same as writing P1 minus P2 equals 0. Okay. Now, it's very rare that we would ever put something in here that's not 0, because usually we're comparing if the two populations are different. It usually doesn't matter if they are very different from each other. It just matters if they're different. Okay. I guess it would matter in some cases. Like imagine if we were looking at the two COVID vaccines and we were comparing those. We do want to know which one's more effective, but even if one is more effective than the other, there's still value in having both of them. Okay. Unless one of them was like so much better that the weaker version just isn't even worth it, right? Like if one of them was like 99% effective and the other one was like 60% effective. If that was the case, we could put in a number that wasn't zero here and just see like, okay, how far off, like is this one 10% more effective than the other one or whatever. So yeah. But that all said, we are going to leave this as zero. And for the most part, we're always going to leave that as zero. We are going to change this one if we needed to, but for our case, we're doing a not equal. So I'm going to leave that one alone and just hit compute. And I get my z-stat. So my z-stat is negative 1.99. So my z-stat is very close to 2. And you'll remember that when you have a z-value of 2, your p-value is going to be 5%. So my p-value is very close to 5%, 0.0466. Okay. All right, so there we go. As far as shading, this is a two-tailed test. So I'm going to shade in this side here and this side here. Okay. And those two add up to 5%. Okay. Or 4.6%, right? All right, next we can compare our p-value to our alpha. So my p-value was 0.0466 and my alpha was 0.043. Those are really close. But looks like my p-value in this case is bigger. So do not reject. Right, for step 5, if your p-value is less than alpha, you reject the null hypothesis. All right, so then we'll write out our claim. There is not sufficient evidence. Now, for yours, if your p-value is less than alpha, then you would say you do reject the null hypothesis, okay? And you would say there is sufficient evidence to support the claim. What was the claim? So I've had some people just write there is sufficient or not sufficient evidence to support the claim. You can't just say that. You got to write out what the claim is, right? The purpose of step 6 is we're writing out our conclusion that we would present to, if the newspaper or our boss or whoever we're performing this hypothesis test for. All this stuff up above, this was all math and complications and you know complicated charts and stuff like that. And some people would want to see this, but most people don't. Most people want to know, okay, what was the result? Okay. And so that's where we translate our results into English. And then after we presented that, if they say, well, how did you get to that conclusion? Then you can show them, okay, it's this and this is my Z value and here's my P value and so on. But most of the time, when I work with people, they want to just know, okay, what was the result of my experiment and go from there. Okay. So I can't just say I support the claim. We gotta write out what the claim was. Claim was that the portion of red M&Ms and proportion of red M&Ms and the proportion of red Skittles is the same. So I say there's not sufficient evidence to support the claim the proportion of red M&Ms and the red Skittles is the same. Okay. So I believe that the so oh wait. Nope, I'm totally wrong. Yeah, I just wrote out what the null hypothesis is. Ugh, is not the same. I gotta change that. Sorry about that. Uh, support the proportion. Red M&Ms and red Skittles is uh, different. There we go. Okay. We're testing, the claim was test whether there is a significant difference between the proportions. So sorry about that. Totally didn't mean to confuse you. So, okay. There is not sufficient evidence to support the claim that the proportion of red M&Ms and red Skittles is different. So I am with a 4% error rate. So that means I'm looking at a 96% confidence. I'm 96% confident that the proportions are close enough that we can treat them as the same. Okay. So I don't support I don't support the alternative hypothesis. Okay. Now I will point out that earlier when I was looking at confidence intervals, my result was that I did support the claim that they had a significantly different proportion. Okay. And then when I did my hypothesis test, now I don't support the claim that they're significantly different. Okay. So what the heck happened? Well, part of it is that over here, I was looking at a 73% confidence. Okay. 73% confidence is going to have is not very confident. Okay. Here, on the other hand, I'm looking at a 96% confidence with only a 4% chance of an error. Okay. So that's one thing. So over here, I was kind of confident that I could say, yeah, they're different. But if you then said, okay, well, I don't want you to be kind of confident. I want you to be very confident. Well, I'm not very confident because I didn't have a big enough sample size. Okay. So maybe I would need to go and, like we calculated earlier, do like 2000 or so Skittles instead of like 145. Okay. So that's part of it is I was using a very big alpha for my confidence interval, right? This is a small confidence level, which means I have a big alpha. This is an alpha of like 27%. Okay. So why can't I just change my alpha? Well, we've talked about that before. If you change your alpha just so that you get to reject the null, then you're increasing your chance of making a type 1 error. Okay. I have a 4% chance of making a type 1 error here, which is pretty small, which is good. Okay. We don't want errors. So you can't just change your alpha on the fly. Okay. So that's the main reason why I have a different result from number 8 and number 13. Okay. At any rate, maybe you did reject the null hypothesis. Good for you. Okay. Because we secretly know that, yeah, the proportions are not the same. Okay. But you need to have a big enough sample size in order to really, show that. So, all right, that's it for the Chapter 11 project. We're not done though, because we're going to take a pause here and we're going to pull out the sample final exam and we're going to look at page 606. So in the sample final exam, we did the first page already. Tonight, we're going to do this second page, and then we'll call it a night. And then we'll work on another page this Thursday, and then we'll work on some more on Tuesday next week. And then Cindy and Elaine, they'll work on some with you as well. So question number 2 on page 606. A country's gross domestic product, GDP, is an economic measure of how much stuff the country produces. Okay. So in other words, it's not necessarily how much money the country has, but as you're working, you produce stuff, whether you're working in a factory or you work at if you are on a farm, you're producing, food or whatever. So total amount of stuff is, how much that country has. Carbon dioxide, CO2, is a greenhouse gas that contributes to climate change, often produced by humans. This scatter plot shows the relationship found between the GDP, which is dollars per person, and the CO2 emissions in pounds per person for a random sample of countries in the year 2018. Okay. All right. So they've done the StatCrunch for us. That was nice. Which variable is the explanatory variable? So explanatory X, that's the X-axis, and it looks like that is our GDP. Okay. And which variable is the response variable? That's the Y-axis, which is CO2 emissions. Okay. How many countries were sampled? All right, I'm gonna have you guys. So who wants to count the dots? How many countries were sampled?
47, it says it right in the summary.
Yeah, definitely don't count the dots. It says it in the results here. Yeah. Hopefully nobody was counting. Uh yeah, they've got all the results that we need over here. Okay. All right. So what is the strength of the linear relationship? So that we look at the R value, but where do we compare that? So somewhere in your exam notes packet, there's a number line that shows this. So I don't want on test day, I don't want you to have to flip around trying to find, where was linear regression. So make sure maybe make yourself a little note of like which page covers which thing. So what page should I be looking at to figure out this relationship? What page am I going to?
255.
255. Yeah. And so it's a good idea to write that down on your 8.5 by 11 piece of paper so you know what each page covers. So this page, page 255, covering linear regression. So they've already done the stat regression simple linear for us. And here's our result. So our R value is 0.85. So 0.8 is right here. So 0.85 is in the strong positive relationship. Okay. And that makes sense, right? Because um, if a country produces more stuff, then they're probably releasing more carbon dioxide, right? If you have more factories, you're going to be putting out more CO2. And even it doesn't even have to be factories, right? If you have a country that has a lot of farms, um, tractors, or cows, they're going to produce a lot of CO2 gas. Okay. So that makes sense. All right. Interpret the coefficient of determination in the context of the situation. So that is here at the bottom. So we do R squared as a percent of the total variation in Y as explained by the least. Okay, so uh, R squared as a percent is 72.9% of the total variation in CO2 emissions. That's our Y value. Is explained by the Christian line. Okay. Write out the regression equation. So that's this one right here. Now I'm not going to write it out as CO2 equals, and then these numbers with GDP. I'm going to use X's and Y's. So Y equals 0.496X plus 211.45. Okay. Um, so technically this is Y hat, but I'm not going to write that. That's fine. Okay. And I did switch the order. You can switch. You don't have to switch the order. That's it's up to you. What is the slope? The slope is the number attached to the x. and interpret the slope in the context of the situation. So if x increases by 1 unit, then y is expected to increase or decrease by approximately slope units. X is GDP. If GDP increases by 1 unit, what are the units for our X here?
Dollar per person.
$1 per person. So if your country makes $1 more, if each person in the country makes an extra dollar, then CO2 emissions is expected to increase, because it's positive in this case, by approximately, and then you write out the slope value, and then the units of y in this case are pounds per person. Okay, there you go. If GDP increases by $1 per person, then CO2 emissions is expected to increase by approximately 0.496 pounds per person. All right, what is the y-intercept of the linear equation? So 0 comma something, and in this case 0 comma 211 or 5. Explain why this likely does not make sense in the context of the situation. So usually they say it doesn't make sense. Here they say it likely does not make sense. Well, so 0 is my x, and x is GDP. So it's impossible for a country to have 0 GDP, right? That 0 GDP means your country produces nothing all year. Everyone sits around and does nothing. Okay. Um, and that's not going to happen, right? You wouldn't have a country then. So, and then your Y value would be 211. So you, even though you sat around doing nothing, you're still putting out 211 pounds of carbon dioxide per person. I guess that's just from breathing. You just all sit around breathing for a year. So that's not going to happen. Okay. Lastly, for the US, X is 61. That's GDP. So $61,000 for the Y. Calculate the Y. So Y equals 0.496 times $61,400. Now, this, by the way, this is how much money each person produces each year, is not how much money you get paid, right? If you are working at a company and you make the company $61,000, they're going to pay you less than that. I don't know how that makes you feel, but that's how that's how society works, right? If you make $61,000 for the company and they pay you 50,000, then the other 11,000 is profit for the company, right? They can't, if you make $61,000 for the company, that's how much stuff you produce. They can't pay you more than that, or that company is going to be losing money. They're not going to be profitable. So, but you know, throughout your entire life, you're going to be producing more than what you get paid for. So I don't know how that makes you feel, but that's just how life is. So, okay, so we're gonna put this in the calculator, figure out what we get. All right, so it's 0.496 times 61,400 plus 211.45. And so that is 30,665.85. That's our Y value. So what do all these numbers mean? Explain what these values mean using context. So the US has a GDP of $61,400 per person. And CO2 emissions of 30,665 pounds per person. That seems like a lot of carbon dioxide. But it's per year, I guess. So, okay. All right. So that's it for tonight. If you have questions, feel free to stick around. Uh, Otherwise, we're going to work more on the sample final exam later this week. Don't forget to do your lecture notes, our last lecture notes, and I will talk to you guys later. I do have stuff for you, Cindy, so don't go anywhere.